So what is Fleek Network? It's a decentralized, permissionless content delivery network, so anybody could join the network, and there's no like central server or central authority that controls it. It scales with demand. It serves Web3 content, so it's agnostic, so that's a good property of IPLD, but it's also agnostic to the underlying storage layer. It's also interoperable with these underlying storage layers, and it offers a low service cost. It's robust to failures and attacks, and it's peer-to-peer. So who is this for? Everyone needs a CDN, but we desperately need one for Web3. At Fleek, we serve websites and storage, and we would be the largest user of the CDN. But beside us, there's video platforms like LivePeer, there's marketplaces, NFT marketplaces, and then there's DeFi front ends, and there's a lot of users that we think are going to use the CDN and be a bit big. So why are we doing this? Simply to accelerate all Web3 content. So I like to view it as Fleek Network, pulling information or pulling storage and caching it around the world from all these storage providers, and we're starting with Filecoin. So let me give you a distribution of the number of requests between storage and websites. We do 80-20, so it's 80% of all our requests are actually storage-based, and 20% are for websites. And globally, 81% of all requests are actually video-based, and then everything else is like websites and gaming, etc. And according to Cisco, and then Cisco also says that 71% of all internet traffic actually goes through CDNs. But even though Web3 traffic is a subset of that set, we think it's still a good metric. Before I get into sort of the composition of our network and how it's composed, I do want to talk about censorship resistance. And I believe censorship resistance is an important design choice that any disruptive protocol should consider when they're designing their protocol. And for us, the goal is to mask any quick communication, and mask it as HTTPS basically. And we're trying to obfuscate the web traffic, we're trying to encrypt the web traffic, and also use QUIC, which we do between our node communication. But recently, we've also seen that QUIC, version 1 is being censored at multiple countries in the world. But we need to all be cognizant of that. Anyways, so here is how the breakdown is of Fleek Network compared to a traditional CDN, where cache nodes operate and communicate with one another, afforded by this content addressable medium, and they can scale their region based on the demand by not having to hop to a central server to get content, and they can also stream data between each other, and then clients can then on the client side get the data and incrementally verify the data, so that they don't even need an authority to verify their data. So it's truly peer-to-peer. So our network is composed of cache nodes, gateway nodes, and origin, which are these storage layers or storage providers that I talked about. And the network operates on this premise that all the data is represented as IPLD, so it's trustless, it's tamper-proof, and that's how all the data transmission between all these different actors communicate on, and that's the medium. So cache nodes set up their own DNS and TLS. They're also responsible for data replication. So they're responsible for saying, okay, I should replicate this data amongst multiple peers. And they're also responsible for routing said data and peer discovery, obviously, like we know, and then cache accountability. So if you serve a cache, you should account for it so you can get incentivized. And then obviously index providing, which is very important because you can announce to an indexer when they have cache, and you can re-announce again when you don't have that cache. And that's kind of the edge node, and then in front of it there's a proxy, and then we have an indexer. So gateway nodes open sessions between themselves and the cache nodes, and that's when they serve requests, and that's how cache accountability happens. They also have, they communicate with network indexers, and that's how, we're going to get into content routing in a bit, but that's how they have an index, and they use a cherry picker based on the geolocation of the request, and that's how they can communicate to these edge nodes. For gateway nodes, we want to have an iterative approach to decentralization because we can pluck it out, like previous talks talked about, and we can incrementally verify the data on the front end using some sort of plugin or Chrome extension. So we use the default content routing, which is like using the DHT, using gossip, but we also have combined or composed consistent hashing, index providing, and Bloom filters, which is something we're getting into right now. And with consistent hashing, that's what I talked about when you can replicate your content amongst other peers. And for index providing, that's where it provides you the fast lookups, like in the milliseconds, so we can know exactly where the content is. And that happens on the gateways as well as the cache nodes themselves. And then Bloom filters are a really interesting topic we're like diving into now, which is a cache node can broadcast its cache content to the set of its peers, and then that's how they can locate their data amongst a local DHT. Also, they can keep a Bloom filter for the nodes in their mesh. So like that's manageable because if your mesh peer n is equal to 8 or 12, that's when it's fine to reconstruct it again. So because it's manageable and you don't have to keep a large Bloom filter. So here's a quick user flow. So you get an endpoint as a client, then you connect to a gateway. The gateway, using its cherry picker, looks into finding a cache node. The cache node returns the car file. The car file returns the data, and then incrementally verifies it. So we also use a consensus algorithm that we're getting into using Narwhal and Bullshark, and that's where transactions are ingested using n number of workers. It depends. It's usually one worker. But then we batch these transactions, and then we broadcast them to the network of nodes. That's where consensus and the quorum on these batches happen, and then that's how the signatures get aggregated, and eventually we know that the availability of these transactions on other nodes. So this is why we originally started with hot stuff, and then we found some bottlenecks there, and that's recently we got into researching about Narwhal and Bullshark as our consensus. So again, I'm going to get back to this diagram. I call it a Dyson sphere of economies, meaning we want to accelerate large percentage of Web3 protocols, but we also want to combine the economics of these protocols and incentivize providers or cache providers from these protocols. So we want to tap into storage protocols, incentivize people, or create an incentive model around cache content. And then the base economic model of nodes would be obviously like how much bandwidth you're serving, your hardware costs, and obviously you need to stake money to participate on a network. And then if you're not running on a data center, then you need to worry about your own electricity and stuff like that. And then you earn Fleek for requests served and bandwidth. So while Filecoin, it has a great concept, which is retrieval markets or retrieval clients, and I'm pretty sure a lot of you guys know already about this. It's very competitive and it's very cheap to store on Filecoin. There's also a Consensus Lab, which is an amazing group of people who are doing great stuff in consensus, and that's where I'm digging into our consensus mechanism. And yeah, there's also IPFS and libptb, and there's many more, and obviously an amazing community. And yeah, they store a lot of bytes of data. That's huge. So by the end of the year, we want to have a large testbed running where 1,000 nodes of cache nodes basically running, 1 million requests per node, and 1 billion requests by the end of the year for the entire network. And we could run it ourselves, but we might need the community to run it with us. And then obviously the metric which a lot of people talk about, which is time to first byte. We do want to target the North Star, which is 15 to 20 milliseconds. But our goal really is to figure out how to speed up content routing, which is very important. I think if we can massively speed content routing, the time to first byte will always be good enough, or CDN level. And then we have missions. So I have some time to explain to you. I actually don't have some time, so I'm not going to explain that to you what missions are. But these stars and how things are organized here is based on Ursa, the internal name of the project, which is a major in astronomy, and it's composed of these 7 stars. And we're starting with mission number 1, and it's Q3. We just finished it with the alpha and content routing. And then end of the year, we're integrating Filecoin, and then our consensus, which is Narwhal. And then we're going to get into QN-1, or just 7 stars. And next year is going to be governance and just tap into all these retrieval markets at Filecoin and other storage protocols. And yeah, what's next for us? I did speak about having to communicate from multiple storage protocols that operate on different blockchains and in different consensus algorithms. So we're exploring threshold ECDSA and how to communicate between these different protocols and doing omni-chain basically. And then something that I'm excited about, and there's a lot of people here and you're going to hear a lot of talks about compute over data, and it's an amazing initiative, and we're kind of starting our part of it. We started it last year with IPFS FAN, and then it's coming back full circle now, and we want to explore creating a modular compute over data framework that COD and Baclau is doing more like cluster-based, which is amazing, and we're getting inspired a lot from that project. But we're also using this framework to create a stateless or serverless framework, and then you can tap it with APIs into a statefulness with CRDTs and databases. And then obviously for a CDN, we need edge handlers, so that would be a good use case. And then SSR, server-side rendering. So yeah, thank you.